So let's talk about learning curves. That's section 2.6, learning curves. And this is polynomial regression has, with a high degree, typically allows for kind of closer fits to the data compared to simple linear regression, right? So if we go ahead and take a look at what this might look like, here is an image of that. And so we have data, which is our blue dots here. And then we have a 1 degree polynomial, a 1 degree model, which is linear lines, a 1 degree polynomial. And then here in green, we have our 2 degree. And then in red, we have our 30 degree.
Does that kind of just say that we currently get diminishing returns with how you go with this? It seems like a very good.
Yeah, exactly. And so we can get diminishing returns with how high we go. And so definitely you could say here that the linear model presents like an underfitted case, right? It doesn't really capture the complexity of the data. So the high degree polynomial kind of dramatically overfits the data. It's just trying to memorize kind of every data point that it's exposed to. And sometimes the data points are more tightly packed than others. So among these, the quadratic model is probably the best, right? So in this instance, right, maybe the quadratic model is clear. Also, it helps that we made the data set from a quadratic model, so it's pretty easy to understand. However, in a real world scenario where the underlying function of the data is unknown, determining kind of the optimal complexity of your model is very useful, right? So how can we attain if the model, so the question we have is, how do we know if our model is overfitting or underfitting? Right? So how do we know if our model is overfitting or underfitting? And we can do that with learning curves. So the answer to that is the name of the section, right? All right, so analyzing a model's performance on the training data looks a little bit like this. So what we're going to do is we're not going to feed all the data in at once. We're just going to feed a little bit of the data in. And we're going to get a learning curve model like this. So here I have some training data, and here I have some validation data. And I have the number of data points in the training set. So initially, I'm going to start with 0 data points. And so I have kind of, well, 0 error, which doesn't really make any sense. But I have like I don't have any error because I didn't train at that model. And as I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I get a mean squared error that goes less and less and less and less. So, but then if I only have, so if you think about what a data set looks like that has maybe 3 data points, right? I can fit a model through that looks very good. But then when I add my single piece of validation training, maybe like 3 pieces of validation training, I can see how different that is, right? And so it makes sense at a small number of data points, I'm gonna have a very small error in my training data because I'm just memorizing what I have. But I will end up with a very large error in my validation data. And so as I get more and more data, it starts to converge and converge and converge. And this is what a good looking model performance looks like, right? I want them to converge because that means that my model, my training data and my validation data both see the same information in the model, which means I'm not underfitting or overfitting. Now, it might mean that you still don't have the correct model selected, but it does mean that your training of the model is correct. So as more instances are added, the model struggles to perfectly fit the data, right? Due to the kind of inherent noise of the data and nonlinear nature of the data, just the fact that you might not have the perfect model. And then consequently, the error in the data increases until it stabilizes, right? Reaching that plateau that we're looking for. So this is a good model. This is a model for our polynomial fit. So let's take a look at what our model for a 20th order polynomial looks like. All right, here's what the model for a 20th order polynomial looks like. You'll note that up until 18, I have absolutely no error because I probably have data set points that look something like this. And I have a model, right, that can completely fit it. Actually, it's relatively interesting to note that on a 20th order polynomial, you can get almost up to 20 data points that have absolutely no error. So if you were to run this through your pipeline at a 20th order polynomial on a small number of data sets, you would have an exceptional parameter come out, right? You'd have an exceptional model. All of your metrics are insanely good. However, if you look at your validation error for this, it's off the charts. It's hundreds, right? It is completely off the charts. And then as you add more and more data sets, right, your training eventually starts to plateau. This is that plateau, right? And your validation is still completely off the charts, right? As you add more and more data sets, you don't actually get much better results, right? Up until about 58 or 60, and then the validation starts to come down. But when you run out of data, you still have this gap. And this gap is really showing an overfit model. So we can all probably look at this model and say that red is overfit, right? Do you agree with that statement? That the red line is overfit. And we just know that intrinsically from looking at it. We can say, oh, there's way too much complexity. It really doesn't capture the model. If I want to make a machine learning pipeline, I need a way to automate this. And a good way to automate this is to just look at the gap in my learning curves at the end of my data set, right? Or I want something that plateaus out nicely. Here, I have a nice plateau. I'm pretty confident that the next piece of data I add to this, if I stop training it and I just start using this for inference and feeding new data in, that I'm going to get an error of about 1.8, right? I am not confident really at all of what my error is going to be here, and I'm very confident that I have just overfit my data. That makes sense? So what do you notice? What could be a saving grace of this overfit data? How could you maybe save this model? More data, right? So more data would save this model. if you could keep going and going and going, a 20th order model might actually model what you want, but you're going to need a lot of data for it. I misspoke before. I apologize. This is for a degree. I'm not sure if I actually said it. This is for a degree equals 1, which is a linear line, right? And this is for, and so you'll notice that we have an error of about 2, and it converges. And then this is for a 20th order polynomial. We have an error so error of about 1, maybe 1.5. So the error is technically less, but it does not converge. So it's not really a stable answer. Now, if I look at what my learning curves look like for a 2-degree model, I get this. So degree 2, I get an error of about 1.2, and it converges. And I get a nice plateau. I don't know, do you count the plateau starting at 10? But I mean, at 40, the plateau definitely gets smaller, right? So somewhere in there, I have a nice stable result, and that's my second order model. And so this is a way to automatically quantify the quality of your model. So